Okay, YouTube, in this video we're going to be focusing on how we can take a matrix that is representing, say, some system of equations and rewrite it into what we call row echelon form. And as we could see from our last video, this row echelon form would be this idea that we could have some system where if there were ones down the main diagonal and zeros underneath it, that is to say that it would be the same as this system that you see right here, then we could easily say that we already know or could solve for the value of this third, say in this case, variable, or the last variable, and then just by using back substitution, be able to solve for the rest of the variable values. So if that's our intent, is to be able to write it this way, because not all matrices or systems come in this form, then really what we're going to be doing is focusing on what row operations are available to us so that we can rewrite this matrix. So just to be clear, we say that a matrix with ones down the main diagonal and zeros below the ones is said to be in row echelon form. Okay, row echelon form is this form that this one is in right here. But we'd say, asking this question, how do we produce a matrix in this form? The answer is truly that we use row operations on the augmented matrix. So we say that these row operations are just like what we did when solving a linear system by the addition method, but difference is that we no longer write the variables usually represented by x, y, and z. So when we're doing this with matrices, what it's doing is it's saving us the trouble of having to, say multiply a whole equation by 2 so we can get things to eliminate or cancel out. And so doing that, you had to rewrite all your x's, y's, and z's. With our matrices, we're going to just skip that altogether. And so it makes it a little bit more streamlined. So these row operations, these matrix row operations, they're also referred to as elementary row operations. But essentially, these are things that we can do in order to rewrite a matrix into a newer form, let's say that's different from the older form, but at the same time has the same solution set. So that's to say that if we had this system right here, we said, what could we do to this system here that wouldn't change the solutions? Well, one thing I can tell you right off the bat is this. Two rows of a matrix may be interchanged. This is the same as interchanging two equations in a linear system. So that is to say, looking up here, we could actually just take our first equation and our second equation and totally switch those around, and we still would have had a system that its first equation would have said z equals -2, its second equation would have said y minus z equals 2, and its third equation would have said x minus y plus 2z equals 4, and we would have just had it switched around. So we can switch two rows around. Now these next two steps, so to summarize here, there are three row operations. The first one is switching two rows. So we can switch rows. I'm going to write this here. Switch row values. Same solution set, so same matrix. And then we'd say the other two moves that we're allowed to make are these. We say that the elements in any row may be multiplied by a non-zero number. This is the same as multiplying both sides of an equation by a non-zero number. So in cases where you may have solved systems before, we say that you can just take a whole equation times a number, and that would still represent the same set of solutions there. So we can scale an equation, and that's what I want to write right next to 2. We can scale an equation by a multiplier. Okay, we call that actually a scalar, but we can take a whole equation times a number and scale it up. And then the last move here, it says that the elements in any row may be multiplied by a non-zero number. So kind of like we just did, we'd say I could take everything times 2 or everything times a -2 or whatever I want. But we'd say, and these products may be added to the corresponding elements in any other row. This is the same as multiplying both sides of an equation by a non-zero number, as in number 2, but then adding that equation to eliminate a variable. So that is to say that we could, if I had something like this, if I had just this, I'm making the system up here, but I had something like -2 plus 5y equals 8. Then really what I could do is I could say, let's take all of this times 2, and then we'll add it to the second equation, because when I do that, I get my x's to cancel right here. So if I were to take 2 times x and add it to -2x, I just get 0 x's. 2 times 2y is 4y, and 4y plus 5y would be 9y. And then we would say 2 times 4 is 8, and 8 plus 8 is 16. We could see that this would have been the equivalent to what this row operation is saying we can do. So we can add a multiple, we're going to list this out in plain English, of a row onto another row. We're going to make a note here. I just kind of ran out of room. We would say that the row we multiplied first doesn't change. Doesn't change. Only the row you added on to. Only the row we add a row multiple onto changes. So we're going to see this in action here, but I want to show you how we can use these row operations to manipulate a matrix so that we can switch around our matrix so that it's in this row echelon form. So we'd say that two matrices, as a matter of vocabulary here, are row equivalent if one can be obtained from the other by a sequence of row operations. So that is to say that we're going to rewrite using these operations maybe a matrix like 5, 6 times, but it's not going to change what the matrix solutions are. So one thing that I do want to comment on is essentially this notation that you see over here on the right. So this is our notation for row operations, but we say that each row operation in the preceding box can be expressed symbolically as follows. So we say interchanging elements in the ith row in the jth column. Essentially, when we write a matrix here, let's say that we have a matrix row 1. We say row 1, row 2, dot, 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 row I, dot, 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 row M, where maybe this matrix is M rows by N columns. And so we'd have, rows here all the way down to the Rm. But we'd say Ri. When they use this Ri here, it's just kind of like the ith row with the jth row maybe. We have a jth row in here, rth row and jth row. So if we wanted to switch these around, we would on the outside, and we'll get used to this, we say, let's switch Ri with Rj. Oh, this is impossible. Ri with Rj. And so if we were to switch those around, we'd still have the same matrix. Now number 2 says multiply each element in the ith row by k, where k is just some constant. That just means we could take everything in a single row times a number, but we would write that as k times that row's elements, and then add k times the element in the row I to the corresponding elements in row j. So in other words, we're going to add, say, k times row I plus row j, but it's only going to change row j. But in every instance, you'll notice that we're using a capital R to recognize the rows that we're operating with. So for the very first time, what I want to look at is just performing some basic row operations without a goal in mind, just doing them. So using these two matrices here, I'll start with doing this one with you here, and then I'll ask you to try these on your own, and then check out your solutions when you're ready. But looking at this here, we have this original matrix here. We have rows 1, 2, and 3. It looks like what we want to do is switch row 1 with row 2. So the way we would write this is, and I would write smallish, is that we're just going to take row 1 and row 2 values and switch them out. So row 1 would be what row 2 values actually were. So 1, 2, negative 3, and then we would get 5. And we would just take 3, 18, negative 12, and 21 and list them in the second row. Now our third row we didn't do anything to. So we get negative 2, negative 3, 4, and negative 6. And so what I want to do is make sure that every time we perform a row operation, on the outside you have to list what you did, and you list it in front of the row you did it to. So since we switched row 1 and row 2, we kind of did it to both of them. In this case, I'm not really going to mind where you write this, but we do need to write on the outside, here's what I've done. So this is what we're doing to tell what we've done. We've done. You have to list your work here so that we know what you've done to your matrix in order to get this. And you would see that it's the same set of solutions as the system would have on the original matrix, just listed a little bit differently. Now letter B here, this is a little bit different. We're going to take 1/3 times row 1. So the way we would write this out really is this: 1/3 times row 1. On the outside we say 1/3 row 1 next to row 1. So that is to say, if we were to take 1/3 times all of these values in this top row here, what we would have gotten was 1, 6, negative 4, and 1/3 of 21 is 7 respectively. So we really would have just been doing that, and that's what we're doing here. So we get 1 is 1/3 of 3, 1/3 of 18 is 6, 1/3 of negative 12 is negative 4, and 1/3 of 21 is 7. So here's our new first row, and we would just re-scribble the other two rows here. You could see that not even having to write the x, y, and z with your system associated with this would be a beneficial thing. So we would say that right here is the resulting matrix we got when we took 1/3 times row 1. So now for our last one here, 2 times row 2 plus row 3. Now this is the third of our possible operations here. And what we're doing is we're affecting, I'm going to write this here, affecting only row 3. So this is weird the first time I show this to anybody, but basically what we're going to do is this. We're going to write our matrix here, and we're going to say that really what we're doing is affecting row 3 because it's the second one that we're adding it onto. So on the outside, we're going to write 2 times row 2 plus row 3 next to row 3 because it is the row that we are affecting. So that is to say that row 1, check this out, row 1 is still 3, 18, negative 12, and 21. Row 2 is a matter of fact, even though we used it to multiply by 2 and dump it onto row 3, row 2 is still going to stay the same, 1, 2, negative 3, and 5. But what we're going to do is we're going to mentally now take everything in row 2 times 2 and add it to row 3. So here's where we got to start thinking. If we took 2 times 1 here, we would get 2, and 2 plus this negative 2 here would give us a 0. Now if we were to take this 2 right here, times this 2, so 2 times 2, if we were to put this out front, 2 times 2 is 4, 4 plus a negative 3 is a 1, so this would become a 1. If we were to take 2 now times this negative 3, 2 times negative 3 is negative 6, and add that to a positive 4. Negative 6 plus a positive 4 is a negative 2. And then lastly, if we take 2 times this 5 here, 2 times this 5, and add it on to what was formerly in row 3, so 2 times 5 is 10, and add that to our negative 6, we would get a 4. So the weird thing to notice is that we've only affected the third row, and it was nice that we did that because now we've got a 0 down here where we're kind of one row echelon form anyways. So here's what I'll have you do. Pause the video and try these next 3. When you're ready to switch in, go ahead and turn the video back on. We'll look at the solutions. So here we get row 1 with row 2. We'd say switch in row 1 and row 2. Let's go ahead and start by writing this on the outside. So row 2 would now become this 4, 4, 12, negative 20, and 8. And so row 1 would now become this 1, 6, negative 3, and 7. So we got negative 3 there, and this is a 1 here, and 7. And then row 3 we didn't affect it all on this operation. We just switched out the first and second row there, so negative 9. So here would be row 1 switch with row 2. Now looking at this second one, 1/4 row 1, we say this is part B right here. And we say 1/4 row 1. We'd better write that next to row 1 since that's the row we're affecting. So 1/4 of 4, that would be 1. 1/4 of 12 is 3. 1/4 of negative 20 is negative 5. And 1/4 times 8 would be 2. So all we did was scale that row down by a factor of a 4th. And we get 1, 6, negative 3, 7 here. We also get negative 3, negative 2, positive 1, and negative 9 in the last row. And so for part C here, what I wanted you to do, or what is wanting to be done here, is we're going to take 3 times row 2 and add that onto row 3. So first things first, we are affecting only row 3 here. Row 3 is the one that's being manipulated. So we say 3 times row 2 plus row 3. We're going to write that on the outside. So rows 1 and 2 are not affected. They didn't get changed at all. So we're just going to recopy them straight up front. It's always my philosophy. Anything you didn't touch, let's go ahead and recopy. 1, 6, negative 3, and 7. Now our third row, we have to take 3 times our second row and add it to our third row here. You can see that taking 3 times this 1 would make this 3 plus a negative 3 would make that a 0, which is really beneficial. We'd say take 3 times our 6, which is 18, and 18 plus a negative 2, that'd be a positive 16. 3 times a negative 3 now would be negative 9, and negative 9 plus a positive 1 is a negative 8. And then 3 times 7, which is 21, 21, say really minus 9, would be 12. So we would get this new matrix right here that we would call its row equivalent matrix to the original. So in the next video we're going to look at is using a method of writing our matrices using these elementary row operations into what we call row echelon form. Cheers.